So now we can start. All right. So hello everyone. Thank you for your attendance. Thank you for attending. Thank you for your attendance. My name is Amna Jabbar, and I will be your moderator of today with SPE in a new exciting scientific topic about rotary steerable systems. And that's for for many motivations why we choose this topic for today. So rotary steerable systems supports a multi-billion-dollar directional drilling market. And that's for many reasons. It enables quality boreholes to be drilled and faster and further than any other method used for drilling. So because of this, this reason, it has also the ability of continuously rotating the drill string whilst the RSS controls the direction of the whole propagation. So to go deeper and in more in details in this topic, we are going to host today Mr. Geoff Downton, who is a Schlumberger Fellow Emeritus. He is going to present to us rotary steerable systems and its current trends and future directions. So to start, before Mr. Downton starts with his presentation and exciting topic, I would like to present him for a few minutes. So Mr. Downton, he is a founding member of SPE's Drilling System Automation Technical Section and a serving officer and a past chairman. He also was a Schlumberger Fellow and Senior Technical Drilling Advisor, resident at the Schlumberger Stonehouse Product Centre facility at Gloucestershire in the United Kingdom. He also, since 1998, he also contributed to the systems and steerable and the development of Schlumberger steerable and drilling tools with interest in automation and control. And also he has over 70 patents. And in addition to all that, he also has a PhD in cybernetics, a master's in control systems, and a distinction and an honors degree in mechanical engineering. And so with all this introduction and background, like heavy background about drilling systems, mechanical systems, and most importantly, rotary steerable systems, I will leave Mr. Downton to present further about this topic. So I hope that you will enjoy. Hello, Mr. Downton.
Okay, thank you.
The floor is yours.
Thank you for a lovely introduction. Can you hear me?
Yes, we can hear you clearly.
Excellent. Right. Okay. Well, thank you very much for inviting me to talk about a technical subject, which actually is something of a bit of a passion. It has been amongst all the other things I've been doing over the years, and that's rotary steerable systems. So I hope to sort of leave the audience a little bit of a desire to know. The presentation is put together to sort of a broad audience, repetition things that you already know, but hopefully not too much. So let's move on to the next slide. There we go. Okay. One thing I must tell was that this was put together under the auspices of the SPE as part of their lecture program. And if you get an opportunity in your careers going forward to spend some time doing the lecture tour, I would really go for retired, a lot of my time in order to do this. So in outline, I'm going to talk about rotary steerable systems. I'm going to cover the steering, benefits, market, modeling, capabilities, case history, automation challenges, certainly not in that order. But at least touch on all those topics. And as a brief and just as a bit of a safety net on understanding and terminology, I just want to say a little bit about the drilling process. Now, I know you're all from a petroleum background and probably know this anyway, but let's make sure that the basic terminology is everybody's familiar with, or at least the terms I'm using means something, so we can follow it through. So a very simple rig. We have the the drill pipe, the drill string, and at the very end is the tool that I'm going to talk about, the steering mechanism. Think of it as a steering robot, actually. It's a nice way of thinking about it. So clearly that is rotated from the surface by the drill pipe to rotate the drill bit. The drill bit propagates the hole. Down the center of the drill string is pumped a thing we call mud. All the people who work on mud don't like that term. It's to call it a drilling fluid. Anyway, mud comes down the center of the drill string. It flushes the cuttings back to the surface. Now, there's a lot of energy involved, and the big rigs could be best part of a megawatt. Driving the rigs, the pumps could be a similar level of power. So a large amount of power is provided at the surface. Not all of it gets downhole, and that's also part of the story. So understanding where the borehole is going and being able to control it, this mechanism, this steering mechanism, is the sort of subject of today's discussion. And in very simple terms, the drilling system needs to know where the hole is propagating. It has no idea downhole where it actually is. It just knows its orientation with respect to the vertical and say azimuth. And this information is sent to the surface by a variety of communication methods. MWD is probably a term that will keep dropping into, which is measurement whilst drilling. But that's a mud pulse telemetry which conveys the information about orientation to the surface. At the surface, there's a controller. The controller looks at where you want to go with respect to where you are actually going. And then downlinked is some steering command to the robot. So the steering robot, the RSS, the drilling system has to be told a certain amount of information about where it needs to go, and this is completed through the surface. Now that's enough of a basic introduction to drilling to get us through the presentation. So a little bit of motivation here. So here at the top is a resistivity image of a slice through a reservoir. Now, the thing to point out is the aspect ratio. You've got something which is best part of 2 kilometers long and with a sort of 3 meter, sorry, in oil field, you've just got to jump between all the units. So feet, inches, centimeters, meters, it all gets mixed up together. So, so forgive the switching between the units as I go through. But you can see that the light color part is the reservoir. This is really where you want the borehole to be placed so you can recover the hydrocarbon. But the aspect ratio is 3 meters, so 3 meters high and 2 kilometers long, and it's not straight, so it goes up and down. So the ability to propagate, generate this borehole, given that this point here might be another 5-6 kilometers to the surface, is really a challenge. And it's one of the motivating factors, one of the things that drove the rotary steerable system in the form that we see it today. So thin reservoirs, so the ability to place a wellbore in a thin reservoir was enabled. In fact, a lot of horizontal drilling has been enabled by the advent of rotary steerable technology. So it's hugely important to the industry. So there are several ways of controlling the direction of the borehole. I'm going to mention some here just for completeness. There's the traditional passive assembly, whereby there is actually no control downhole other than the driller's understanding and knowledge of how the weight of the drill string, gravity, friction, rock properties, the formation, all combine to give a certain capability to control the direction of borehole propagation, mostly in build. Drop in build in the vertical plane. Sometimes if they're really good, they can start to work in azimuth. But this was the traditional way of method of doing it, and would not enable everything that we see today in terms of horizontal drilling. So the vent housing motor came along based on originally there were turbines, and then they gave way to the Moino motor principle, whereby the drilling mud that I mentioned, the drilling fluid, is pumped down the center of the drill string. Goes through this rotor that rotates the drill bit. So the nice thing about this is you're rotating from the surface from the drill rig at say 100 RPM, and the mud pumped down the center can bump this up to say another 150. So if you get 250, maybe 300 RPM drill bit rotation, which is all good for borehole propagation and drilling fast. but also the bent housing motor, when putting a kink effectively in the bottom mold assembly, means that you can point this bit. Now, it's obviously quite tricky. You've got kilometers of drill string to rotate. The pointing direction of the bit requires a certain amount of skill. And ultimately, and because when you're pointing this assembly, this is not rotating, so this is all stationary, all the way up to the surface, 6 kilometers away, or however far it is. So you're pushing this drill string in the direction that you hope that this bend happens to be pointing. And that's great, but there comes a point where you can't get the weight transfer from the surface to the bit, so just can't get the ROP. So there is a fundamental limit beyond which drilling and steering with a mud motor takes you. We can't go much further beyond it. And so lots of people, lots of innovative ideas to put in things that shake axially and laterally just to break the friction, so you can actually push a bit further. And also with surface automation, the ability to use the rig itself to break friction by rotating from the surface one direction then the other, but not so much as to actually disturb the pointing direction, just to try and break the friction to the surface. So these have gone a little way to increasing the range, but ultimately we end up with necessity is a mother of invention. So rotary steerables came along in the late 1990s, and here you have, and there's many different forms, and I'll try and give an overview of all the different forms in a few slides. But basically you have the drill bit, which is gouging, cutting, chipping, borehole, everything is rotating here. But right at the end, say within the first 3 to 6 foot, or say within the first meter or two, but also it could be pointing as well, or it could be a sleeve which is non-rotated, which is pushing laterally. There's many years, there's the different ways people have conceived of putting together a drilling system. So this type of device is what we're talking about. Now, the interesting thing is that one time when the rotary steerables came out, people thought that they would sort of do away with the bent housing motor for steering. But what happened was that people got rid of the bend and put the mud motor on top of the rotary steerable system. So here you had a sort of powerful combination of lots of RPM and the ability to steer without ever stopping. The problem with the bent housing motor was you had to stop in order to choose the direction. With the rotary steerable, because all the control systems that go on the side here allow you to steer dynamically whilst you're rotating, which means you can always rotate, you always get the weight transfer to the bit. And I'll say a little bit more about that later on. So coming back to the mud motor again, here's the mud motor with the kink. Some work was done some time ago to look at when you're drilling straight ahead, you have to rotate the whole assembly. So this sweeps out an arc and makes the borehole slightly larger. And so you get an overgauge, larger hole, orbiting motion of the bend. So you end up drilling a hole which is engaged, more closer to the bit gauge, and so you get this step in the borehole. So this was a nicely controlled drilling test grid drill bench, with only a few drill string behind this. This hole looks a lot more ragged than we've we managed to demonstrate here. So these ledges build up, and this sort of zigzagging motion builds up, which all adds to the friction, which prevents which limits how far you can drill horizontally with motors. So I want to say something about the different steering methods. Now, it's quite different. There's a lot of hybridization between these techniques, but these 4 non-rotating rotating straight through. Bit is rotating, so rock actuation. It's pushing off to sort of one side in order to steer in a particular direction. So the nice thing about this is that you can put your sort of actuation on this. It's not rotating, it's static. In fact, in reality, it's always rotating because there's a frictional drag and everything moves around. So it will be moving to a certain extent. And so the pads that you have to compensate for this rotating motion, which is something that can be done. So that's one method. So you're pushing off to one side. Rotating push is where everything rotates. So this is a little bit more difficult to appreciate what's going on, but basically this is rotating. Even actuation for push in sequence. So you have to synchronously modulate the pad pushing in order to achieve a particular direction of steering. Now, the pushing is fine, but there are certain advantages by actually pointing a bit. So here, and again, you have a sort of similarity whereby the evolution of the tools, where you have the non-rotating sleeve, wherein you engineer a bend. In other words, you have a pointing, either you're flexing a shaft or bending a shaft or pivoting a shaft in order to point in the direction you want to steer it, and you control the direction of pointing within this within this non-rotating sleeve. And again, you have the same challenge. If things are slowly rotating, you've got to keep on, as it were, accounting for that rotation to keep you pointing in the direction you want. And it's highly reliant on this sleeve being well behaved. And at the other end of the story is we have a rotating push where everything is rotating. So this is where, so even your contact point, your first contact point behind the bit is also rotating. And that servo inside is also working at 200 RPM in the opposite direction to maintain the bend in a particular pointing direction. So there's quite a bit of hybridization that goes on between these various techniques, but these are the basic four approaches. And to, over time, they've all managed to be able to show that they can work to a certain extent, but there are sort of key differences which lead to generally the pointing systems are really quite difficult to engineer. They tend to end up with good steering performance if you can control the pointing direction, but they're mechanically more difficult to put together and tend to be a little bit more complex, though there are many advantages from a steering point of view if you can pull it off. By and large, the market, and certainly is evolving in this direction, is some variant of these where you have non-rotating sleeve or everything rotates. If you go back about 15, 20 years, the approach and only one group was doing this. Over time, what I've seen is there's been a general evolution towards everything rotates, because there are certain advantages in being able to do that if you can achieve the control that's necessary to do it. So there's general mutation over time between towards this, although there are some excellent representations for both techniques. These are more challenging, and there's probably only one left, which is a really good example of how to steer by pointing techniques. But by and large, they're the basic techniques. And another image from a borehole that was drilled by Everything Rotates drilling by a rotary steerable system, so 15 degrees per 100 foot curved here in these blocks drilled by this system, as compared to with a motor. So these ledges build up, and also the zigzag motion builds up to limit the ability of how far you can drill. In fact, this slide here is probably older than the audience. It's more than 20 years old and has survived multiple updates to Microsoft and changes of computer. It was put together in the late 90s, and it's still true today. And it sort of captures why the extra complexity and cost of using a rotary steerable system pays off in many applications. So the nice thing, the first thing is you've got the ability to control the direction of steering whilst everything rotates. And that leads to, as I've shown you in the previous slide, a smoother hole. The smoother hole means that you can extend the reach, and so you can drill further, which means you need fewer wells. It's also a good thing for putting in completions. What you don't want to do is put your electric submersible pump in, because it lasts very long. So the ability of a smoother hole when you work over is easier. And the only reason you're ever going to do any of this is because you want to be more efficient, less cost per barrel is always the bottom line of this. So continuous rotating also means there's less drag, because everything is, we break the friction, which allows you to get the longer extended reach without excessive drag, which leads to the ability to drill from a fewer platform. So when you're developing a field, rather than having lots of drilling rigs all over the place, you can have one platform, but you can drill out further. And there's quite some complicated patterns that have been generated over the years to exploit a reservoir. And also from the continuous rotating means the cuttings don't build up. This is a problem when you don't rotate the pipe. You plug off and you give rise to other kinds of get stuck. The risk of getting stuck is something that drillers always worry about. Recovery, fishing exercises to recover bits that you can if you get stuck. But cleaner hole means less stuck pipe, means higher average and instantaneous ROP, which means you can drill faster for the same cost, less cost per foot. Again, this all adds to less cost per barrel. Now, this was put together as part of more than 20 years ago. So there is actually some key thing which is very relevant to today, which is missing. So hopefully I can, if you can guess what that is before I get to the end of the presentation, it'd be great. And if I forget to mention it, someone please remind me to do that towards the end. So they're the benefits of rotary steerable. So again, industriality. I think that put rotary steerable on the map in the UK, in Dorset, called the Witch Farm, where they were trying to exploit a reservoir which was in an area of outstanding natural beauty. There was a bird sanctuary. So they hid the rigs in the forest, basically. It was not visible to anyone unless they were going to look for them. Couldn't see them, couldn't hear them. But gradually they drilled out further and further, and they got to a certain point where they could, this is in the early days of mud motors, bent housing mud motors, they could only get so to reach. That was done by one of the earliest rotary steerable systems. It's still very unreliable, 100 hours or so of reliability and multiple runs, but it was literally the only game in town to drill out that far, to get to the 10 kilometre to fully exploit this reservoir. Now, loads of other things had to be done right as well to achieve that. It wasn't all down to rotary steerable, but it was part of the build, as it were. It had to be in the mix in order to achieve that range, and that really put rotary steerable on the map. And from that time onwards, no one looks back. You know that from that point forward, rotary steerable had a role to play in reservoir development. So what we wanted to do in terms of steering, our forefathers had ideas as what they wanted to do in order to achieve longer reach, but there just really wasn't the technology around. So a lot of things came together in the late 90s, early 2000s that enabled rotary steerable to take place. One was, it's a hellish environment downhole. When I worked in the aerospace defense industries and worked on environmental qualifications tools, what we do to our drilling tools downhole is no comparison. It's way, way more destructive in terms of shock and vibration, and your systems will fall apart in no time at all unless they're well developed and developed specifically for that kind of environment. Robust electronics, the advent of the processor, a robust processor, downhole intelligence. Some of the early rotary steerables use the same processes out of washing machines, actually, in order to close the loop down, downhole. And communications, one of the real advantages of rotary steerables is that you achieve your control by talking to it. You talk to it through the mud pulse telemetry, you ask it things and it tells you things. And in the end, information is far more versatile than trying to do that with mechanical levers. You know, that's a limit to what you can do. And so this was one of the key hidden insights that come from telemetry and the ability to have the downhole electronics. Robust sensors, so aerospace and defense provided the range of sensors, the inclinometers, the magnetometers, the accelerometers, the shock sensors. All these things have their origin in aerospace industry, which was now, as it were, tough enough to be taken downhole. Closed loop control, an area that I'm sort of interested in on the sort of whole closed loop story. Servo actuation and power. These pads or this pointing and whatever goes on downhole is basically a servo, or multiple servos in many cases, are needed to achieve the control. And a story which never goes away, despite all these high-tech things, is actually materials advance. The amount of shock and vibration and abrasion that goes on is tremendous. And it just gets worse as we are able to drill faster and further. And so materials advance, the search for the right type of material and its right use is key to. So all these things have to come together in order to achieve rotary steerables. So in terms of general capabilities, so here's a picture we took some time ago, about 2005, and it shows the world's smallest diameter rotary steerable and the world's largest rotary steerable. So this was a 3 7/8 inch rotary steerable system with a 26-inch system. So the technology expands a broad range of borehole sizes. Today, you need systems at least capable of maintaining a curve of 3 to 15 degrees per 100 foot. Because you need to be able to steer and follow a particular trajectory. Temperature capabilities have to be at least 150, and now that's becoming telemetry. So the pressure, hydrostatic pressure, the crushing pressure of the being so deep with the hydrostatic head of the drilling fluid, at least 20,000 psi for a reasonable system, and some deep water pressures in up to 35 and beyond, actually. So the system needs to be able to talk. You need to be able to talk to it. So the telemetry link with the surface is absolutely key. Its ability to tell the system which direction I'm going, what is my dog leg, what is my inclination, the ability to sort of you can hold loop. Now you need to be able to hold azimuth and inclination, and the more advanced systems have been asked it to do 10 degrees per 100 foot, and it will find that curve. So these are part of the evolution that's taking place in the technology. Because of the high shock and vibration environment, drilling mechanics is key. In other words, measure the shock and vibration, understand how the drilling parameters are being sort of propagated down to the tool, because you can end up the tool being smashed literally with the high, hundreds of Gs for hours on end are not good for any piece of mechanics. It needs to be combinable with a mud motor, so the ability to rotate everything beneath the motor, which is also a challenge for some systems whereby you're spinning at higher speed. It becomes more, your control systems become a little bit more interesting when you're trying to maintain toolface control, and some idea as to where you are, because you're very close to the front end of the system. You're into the new formation. The gamma ray to sense where you are with regard to bed boundaries is a key piece of equipment that's now required within these systems. So this is just generally, you have to have these in place before you can even enter the game now in rotary steerable systems to some level. So real world effects, so the rotary steerable must steer regardless of a whole laundry list of things that's going to stop you from steering. The BHA has a particular stiffness, weight, and where its touch points are all influence the extent to how you can steer and direct the direction. There is a natural tendency within any rotary structure to spiral, weave, drop, walk, or build. In other words, it won't necessarily drill straight. And left to its own devices, it will go off and do something which is based on all these effects. And rotary steerable has to, as it will contain that, and keep a lid on the natural tendency of where the system wants to drill. The rock bit interactions, rock is not uniform, it's heterogeneous, you push the system all over the place unless you're controlling the direction. The properties of the mud will influence how you steer, the lubricity. If you're driven by mud, the mud properties are also important to you. I think which hurts all rotary steerable systems, about all systems for that matter, is when the hole goes over gauge. If it washes out and there's nothing sensible to push on, that will also hurt you. The wrong drilling parameters will also mess up your system by damaging it. Drill string dynamics, you've got a long, flexible assembly, big spring that's kilometers long. It has its own environment. It lives its own life in terms of the dynamics which are going on. And of course, you've got the system right at the end, so it's sort of, it can be flipped around quite dramatically, depending on how it's locked into the formation. Spatial locations, these are all super critical to your ability to steer. Delays in control and communication can also upset the steerability, which I'll say a little bit more later on. So you're involved in a lot of mathematical modeling of the drill string and all its components, understand the torques, the loads, the bending behaviors of the system as it steers. There's a lot of electronics, and so it's natural to get into the whole area of hardware in the loop to demonstrate that your algorithms, your software is actually working properly. So you drill the well electronically, but also with the control system as part of your control loop. And as you've probably seen similar things from where they test cars, but that is also becoming part of the technology for rotary steerable development. And also you've got to be able to demonstrate in a very low cost relative to a real rig environment that you can steer in a way analysis, modeling, and a staged series of drilling tests. You would drill blocks, then you may go to a test rig, and then you confidently go to a client, and so you start to build up your confidence with the system. And it's a long road. So if you're starting out with a new system, there's a huge number of things that you need to learn. It takes years and hundreds of hours of drilling experience to polish, thousands of hours of drilling experience to get the system really polished. So one of the things that has happened, as most people will be aware, is the horizontal drilling has been enabled by rotary steerable. And if you look at this plot here of the horizontal reach of a well versus the vertical depth, this outer envelope here is largely driven by rotary steerable systems. The ability to, say, drill out to near on 15 kilometers horizontally can only be done with rotary steerable systems. And even vertical is, in order to be able to ensure that your well is perfectly vertical and not full of kinks, also needs to be well controlled. So this is, this envelope is constantly evolving with the evolution of rotary steerable systems, and obviously enables a great deal of the horizontal well, certainly offshore horizontal well development. So in terms of the market, so normally I present several slides here, but I think I could condense it down to a straightforward insight. So if you look at how much globally is spent on rotary steerables versus conventional drilling, which is not non-rotary steerable markets, Then in terms from about 2005 to 2019, it grew from about 20% to 75% of all spend. So it just goes to show that, you know, the advantages of rotary steerable systems has been progressively recognized as you go forward. From today to forward, it's held at 75%. What has been remarkable is that this growth has been steady, irrespective of the dips that we've seen. You know, the 2008 crash, 2015, and most recently 2019. These dips in spend, this distribution of spend is still being in favour of rotary steerable. So even when things are tight, the advantage of, you know, of being able to complete a well more efficiently and more certainly with the rotary steerable as opposed to any other technique has been something that's been is more widely recognised has been over time. So an area which has always been of interest to me, and we get into the sort of mathematics of the drilling process, is borehole propagation. So one of the things that I've been always interested in is how is it, you know, how is it we can relate the parameters of the system to the way that the system steers. Now we have a large number of detailed mathematical models, but here I was looking at more of an analytical approach, and the advantage of that is if you're putting a control system around a tool, you want to have a sort of a model of the system which is lightweight, basically. So some of the things which are important to understand about steering is steering geometry. So here is a push the bit system, and here is a point the bit system. So the first aspect is in order to achieve the dogleg that you require, and the big challenge over the years has been the ability of systems to achieve higher and higher dogleg, is the geometry. First you've got to be able to establish the geometry. So a simple rule which works quite well is the dogleg capability, number of degrees per 100 foot or radians per meter, or however you choose to express your curvature, is geometrically related to where the bit is, to where this contact point is, and where the first pivot point is to wherever you think it is. And the dogleg is 2 times this eccentricity. This eccentricity is the difference in centerline of the BHA and the centerline of the borehole wall. And it doesn't matter whether it's a push the bit or a point the bit. With a point the bit, you can achieve a larger offset simply because of geometry, but nevertheless that still relates to the doglegs. It's achieved geometrically, and this is important for the story of how things are evolving currently, is the way things are. So this very simple formula has carried forward and is relevant to the way we think about systems going forward. So bit anisotropy. So that was geometry, but you can't achieve a geometry unless you can achieve the required force. And you can't achieve the required force unless you understand what is required at the bit in order to propagate the hole in a particular direction. And so to a very first order, this is like the first term in a very long expression, but to a first order, you can think about bit anisotropy, which is basically the mismatch of drilling ability between a bit drilling sideways due to side loads and the axial loads. So the axial force on the borehole gives rise to a certain ROP, the reactive force on weight on bit. So a lateral force on the borehole is going to give you another, and that's achieved by some reactive force on the borehole. And it gives you an ROP, a lateral ROP. So if you look at the resultant force on the borehole and the resultant of the ROP, they're not the same. You know, the bit won't go in the direction that you're pushing it necessarily. And this relationship between the mismatch between steering is called bit, and it has this relationship here where the angle is the anisotropy, which is this non-dimensional number, which is the first term in a long complex expression, which is related to the lateral weight on bit divided by axial weight on bit. So in order to change the direction of the borehole with respect to the axis of the bit, you need a certain side load, and the amount by which you can change the direction is related to the side load itself and this non-dimensional number, which is a feature of the bit and the rock and a number of other things. So if you come back to the same pictures we saw before, and we look at steering force, you can see that the contact force here is related to the dogleg that you want to achieve geometrically, and some parameters which are to do with geometry. You've got anisotropy term here, divided by weight on bit, which means that the dogleg is it were proportional to anisotropy. If this doubles, then this should double. If this half, you compare that to a point bit system, then you have something interesting going on. Is the dogleg is still related to the contact force, which is in many cases reactive force due to the bend going around the curve. So the formation's got to be able to withstand that force. But if you look at it in terms of the anisotropy, this L2, because L1 is invariably much shorter than L2. So L2 here cancels with L2 here. So you end up with the effect that the dogleg performance of the steerability of the steering direction of a point-to-bit system is less sensitive to variations in bit anisotropy, which is one of the main reasons why people, in effect, use point-to-bit systems, is that they're less sensitive to this aspect of the bit and the formations. But the downside is this is technically more challenging to achieve in a rotary steerable system. So it also leads to where things are going currently. So by and large, the trend is towards a sort of a push the bit system, where you have some actuation which is pushing off to the side here, and you have essentially straight. This, if you took a sort of a vote as to what the new systems were coming along, they're tending to fall into this sort of category where you have some actuation, some kind of bit, and some pivot point. So as everybody's looking for higher and higher doglegs, so you can see here that this is related to the stroke of the actuation, or whatever mechanism you've got here to produce this. There's L1 here. If you can make L1 small, let's move this further and further and further to the front end, so you can increase your dogleg without having to have necessarily a more complex actuator, which gives rise to a longer, further push. And so that's sort of an interesting evolution. We've seen this in mud motors as well, where the bend is getting closer to the front end of the system, and here the actuation is moving closer to the front end. So there's a natural evolution which is going on based on this very simple formula. And similarly for the dogleg, one of the challenges as you're drilling faster, the higher ROP, is if you're pouring weight onto the system, it tends to depress your dogleg capability. So bit design, which allows you to go for higher weight on bit without necessarily, or as it were, working to increase the anisotropy, is how you do that is all part of interesting aspects of bit design, but there's actually a fundamental limit to which you can increase your dogleg by making this more and more aggressive, which I'll say a little bit more later on. So, one of the early problems people faced was the positioning of this actuator, this push. If it's close to the front end of the system, that's fine, but it's too far back in some of the early designs, you end up with the BHA bending, so you're pushing in this direction, but it's pointing the bit in the wrong direction, so you weren't achieving the dogleg that you would like. So one of the remedies might have been to increase the aggressivity of the bit, in other words, make it more laterally aggressive. But there was actually a fundamental problem in doing that, which is best captured by this plot here, which is to do with borehole stability. So imagine a flexible drill string. Not actuating, not a sort of rotary steerable, just straightforward, as they say, dumb iron, which is a flexible shaft and two stabilizer, centralizer positions. What you find is that this can either drill a smooth hole or it can drill a spiraled hole, and there is a simple relationship which to do with positioning of the actuator and also the stiffness of this assembly. Some aspect to do with the length of the system, which is the overall length, the geometry, times the anisotropy and weight on bit. So again, this is actually a non-dimensional number. This is a non-dimensional number. And if you plot out where it's stable and where it's not, you can see mathematically, even for a simple system, we not only control whatsoever in heterogeneous formations, no other reason can be sort of brought to why these things happen. But if these parameters here put you in this region, then the system is stable. But if you have overly aggressive, this is the problem with having overly aggressive bits and very stiff systems, increasing these numbers push you into this zone, which is where you get the instability, where you can get sort of natural spiraling can occur, where it just self-propagates. If you look at this as a feedback control system without just borehole kinematics, then you can derive these equations, which I show in a paper that I put together for the SPE, which I'll reference a bit later on. So another area where things can go wrong in terms of stability is the ability to close a loop around an actuator. So again, any rotary steerable system doesn't have to be any particular type. The steering mechanism could be push, could be point, not relevant for this discussion. But you have an inclinometer which measures your inclination, basically accelerometers, or magnetometer can work out your azimuth or direction. System receives some target, say inclination or azimuth. It uses this measurement. The measurement works out an error. The error goes to a control loop. This is a control loop within the steering system itself, and that does something to the actuators. It modulates them in a particular way to give your pushing direction. So you have this closed loop. So you tell it an inclination and azimuth, the system will lock on and try and hold that orientation for you. However, there are sort of fundamental issues and problems with this. So if you try to do this too tightly, so if you have a sensor that's too far back, it's not giving you the true steering direction, because this starts to flex and it's not pointing. So this isn't pointing in the direction the bit is going. If you have too high a gain here, you end up with a system which can be unstable, because the actuator and the bit and the sensors are spatially separated. And again, if you look at the kinematics, you end up with a control system which has got inherent delays in them, spatial delays, not just temporal delays. And by having a very tight loop, it can start to weave. And if there's too much time spent in deciding where to steer, so too much filtering, or maybe this information is sent to the surface and it's sent down and you carry on drilling and you're using the last inclination or azimuth value, you're out of sync, and again you can end up with this weaving behavior. And we see this with some systems, particularly where there's magnetometers involved, where they try to move them further away from the bits. The magnetometer is a long way away from the steering system, and you try to hold an azimuth, and you end up with something which is weaving around the direction that you want to go in. So this aspect of the way systems behave has always been something that's been of interest to me, and this led in part to the putting together of this paper at the bottom here, Drilling and Completions Journal, Systems Modeling and Design of Automated Drilling Systems. So basically, if you've got a background in control, mechanics, or electrical engineering, and you're so comfortable with Laplace transforms, then this allows you to take any drilling system, any steerable system out there, and convert it to a form which is basically a transfer function, which allows you then to do other things with it, like put a control loop around it. And it also breaks the system down into things which are sort of understandable in their own right, like the shape of the borehole, the offsets and stabilizers, whether it's got a bend or not, the self-weight, the gravity effects on the BHA as it sort of distorts and sags within the system, and then your actuator forces as well come into the system, which allows you to start thinking about the behavior of the system at a sort of control system level, which is important for when you get to automation. So there's a list of papers here, which I'm sure we can have further comments, but you go deeper into the non-linear effects of behaviors, which are, I've just talked about the linear side of the story, but it's highly non-linear and stochastic, and all these things need particular attention when you get into the details. So this is just just a veneer, a surface introduction to what's going on. So in the early learnings have been to do with automation. So again, 15 years ago, put together a closed loop system where we have in fact, when coming from the aerospace, the nuclear industry, where closed loop was sort of natural, when I saw rotary steerable, I couldn't understand why it wasn't already a fully automated system, because you have a system that wants to be told what to do, and so that's obviously you can automate it. And here was an example where you have this steering system. It's sending an sort of MWD signal, which is a mud pulse telemetry, to the surface. The surface looks at a well plan, works out where you want to go. Then there's a command sent down to the system, and you could close the loop. The driller was in the loop to sort of accept or reject whether the steering commands was sensible or not. So in principle, this worked, but the downside was that everything, literally everything outside the rotary steerable was not set up for closed loop control. And the delays, the interfaces, every rig was different, every setup was different. And so whilst this has been a capability for some time, it's never really been exploited until now. And so now if you look at the literature, you'll see that closed loop control is now becoming, through the surface, through the rig, much, much more common. And the ability to speed up the process, to make decisions faster than a human being can, in order to close the loop, is now something which is happening. It's happening in hopefully a big way. And you can see this in the literature. So I went back and looked at One Petro publications back to about 2000 or so, and just looked, very crude, not scientific at all, but just looked at the number of hits that mentioned rotary steerable. And you can see from the early days of rotary steerable, go on, and each year there's more and more and more on it. But if you look at the combination of rotary steerable automation, there's, even though this has been something which is inherent in the way these systems operate, really nothing until there's this uptick. And so, and I've not done it recently, but you can run through it again. But I'm sure that we're going to be up here now in terms of putting together rotary steerable and its full potential as an automated system. So in terms of challenges and opportunities, so one of the big challenges that have faced all drilling actually has been the advent of factory drilling, shale drilling, the ability to drill vertical, curve and natural in one go at high speed, lower cost, with good reliability. This has always been a sort of a battleground between rotary steerables and mud motors, which one is best, most suited for it. And for me, it's always been an interesting area to come up with improvements to the rotary steerable that allows you to enter deeper into the mud motor market. And one of the challenges with the mud motor, one of the advantages of the mud motor is it can do the curve, do a very tight curve. However, if you're zigzagging down to the vertical, then the curve, often you have to sort of pull out and change the bend, because you still want to steer sort of, in the lateral, but you don't want to rotate this big bend because you trash the mechanics. And so the ability to have something which does the vertical curve and natural has been a thing that the whole industry has been aiming for. And now you're seeing it with rotary steerable systems that are able to do that whole curve in one go without stopping. So ROP and reach trade-offs. So even in the sort of the US land, what was once deep water requirements, the laterals are going longer and longer and longer. And so the gap between what you can do with a rotary steerable and a mud motor is beginning, bent housing motor is beginning to stretch. Higher double exit, higher OP, higher weight and bit. There's been this evolution of bit technology whereby as you're getting into the nitty gritty of the bit design, but basically the cutters themselves, this man-made diamond which is used to shear the rock, that's been evolving in its terms of its shape, the ability to now not just shear but plow through the rock using diamond 3D shaped cutters as opposed to flat cutters. It gives rise to higher speeds, higher torques, higher loads. All these things are things that the rotary steerables got to cope with, and also has been driven by mud motors. Mud motors are still very much part of the picture, but now they're driving the whole rotary steerable system. So they're becoming more powerful. So evolutions again in longer motors, thin wall motors, which create a ferocious high shock and high torsion environment beneath the motor. So the high frequency torsion oscillations will throw electronic components off boards, fatigue, a huge amount of damage. So that's become a challenge, one of these challenges that rotary steerables have got to cope with now. You've got to be beneath the motor, you've got to stand high shock and vibration, you've got to live with high torsional vibration. Drilling automation is the big thing that's coming along. So as with any automation story, you aim for consistency initially, you get consistency. Once you've got consistency, you aim for efficiency. That's the good way of doing it. You're seeing this now, where people are using automation to getting comfortable with it and then going faster and faster and faster. Early days, long story still ahead of us on this, but it's certainly now, as I've retired, I can see that it's now it's now taking off. So efficiency, consistency, trajectory control at speed. One of the areas which is key for drilling automation generally is knowing what's going on downhole. Now, the communication between surface and downhole compared to most automation control loop stories is really poor. We're talking about bits per minute communication downhole and bits per second to the surface. So in terms of conventional control systems, it's way it's difficult, and that's actually led to the evolution of what way tools are downhole, because they've had to cope with very low communications. But advent of something like wide drill pipe telemetry, whereby at the extra cost and all the other things that go with it, but the ability to communicate downhole, this high-speed communication, is one of these disruptive futures, whereby if you now start evolving systems that take advantage of this, you ask the question, well, what are these systems going to look like downhole in the future if this takes off and becomes commonplace? Safety with any automation system is key. The man is out the loop, relying on the system doing things for itself. You don't want wells drilling into each other, so that whole area is, again, important to take on board with any automation story. And of course, it doesn't escape the whole story to do with data analytics, things on the edge, cloud, AI, more recently, the whole sustainability question. So all these things are beginning to wrap themselves around the rotary steerable technology, and particularly on the automation side. So this is this is still early days, still formative, but there are some good examples now of how these things work, particularly the data analytics. I've been quite surprised in the way that can reveal things about the way your system behaves that you hadn't appreciated, things that you'd missed from the model was there in the data, but you need to see it thousands of runs before you see this sort of trend emerging. So there's interesting things here. Also, a deeper understanding of the physics I think is there somewhere in the whole data and analytics story. So forks in the road, this is my last slide. So if you're going to ask where we're going in the future, if you were to take a majority vote, it looks like push the bit is where most of the newcomers are going in some form or another, or displace the bit. Steering actuation, so the three main, so the thing that is controlling the actuator, whether it be the pressure drop across the motor of the bit, you're talking about 700 psi, many kilowatts of mud energy can be used to control the actuation. So you have mud actuated steering devices, you have electrically activated systems which do the control by using electric motors. You can have oil actuation using pressurized oil in order to control the system. Again, if you were taking a majority vote where people, people evolving, there's been a sort of mud, a lot of people are now looking to mud actuation, but oil actuation is still in there. The one that's less of, because I think it's more challenging, but I think for where the future may well be, may reside downstream, is the electrical side of the electrical actuation. I mean, it's more difficult to pull off, but again, with everything goes electrical eventually. So somewhere in the future, electrical actuation is going to play a part, but not immediately. Guidance systems, so I didn't really get into where all the sensors were placed within the steering system. They can either be strapped down, which means they're going around with the bit, or they can be on a stabilized platform which is isolated from everything that's rotating And that platform can either be on the inside of the drill string, which is roll stable, it could be on the outside, which is the non-rotating sleeve approach. And there's pros and cons in all of them, and it's probably not not the right time to get into the detail. So surface versus downhole intelligence. So processes are becoming much more computed, dictated by the speed of communication from surface to downhole will have that pressure influence. And the other thing, this is my final point, is the extent of systems integration. I mean, historically, technology has had little silos that built, people that build bits, they do motors, they do LWD, they do whatever, and they're working together. But what we're finding is there are advantages as things come closer and closer together, this extent of integration. And some of the exciting things is how do you get on and integrate this? And an example here is the bringing together of, say, the bits and steering, which have been traditionally separate. You have the bit and steering actuator, but there's a lot of advantages in bringing things together, especially if you common up on features. And it's probably the latest evolution is what's called an at-bit steering, whereby you have the steering actuator not sort of displaced in the separate assembly, but now as part of the steering system. And again, there's a lot of advantages in being able to do this, but it's challenging because you're now having systems which interfere with one another. Bits are designed separately from actuation, but now you bring them all together. So it's a difficult thing to pull off, but it also has the advantages when you can. And you could have the same story, the same sort of thing happening for all the other parts within the system. So I think this is one of the exciting areas for this technology going forward, is this ability to bring things together in a sensible way in order to achieve things that go faster, lower cost, and so on, things that we're looking for. So that's my presentation. Thank you very much. I hope I've gone over time, so I apologize for that. So.
Thank you so much, Mr. Downton, for your explanations, or theoretical explanations and mathematical, also for data insights. We have a couple of questions from our audience. But before we dive into the questions, I would like to clarify that this session is recorded. So is anyone, if anyone of the audience you're feeling not feeling comfortable with opening the mic, you can ask in the chat. Otherwise, if your question is explanation or more, or it's a long question, you can raise I will ask the question again.
Sorry,
how is the data being transmitted to the
I accidentally muted myself.
That's okay. Sorry.
I think it was still running with the laser pointer, and I did something. Right. Okay, so sorry. Please question again.
Yes, sure. So the first question is that how the data is being transmitted to the surface, like what is the principle of transmitting the data to the surface?
There are no wires, unless very, very modern latest systems, but there are no, basically there's no wires. So how do you actually get information backwards and forwards? And there's been a number of techniques. The one that sort of evolutionarily has evolved to be the common approach is what's called mud pulse telemetry. So you can imagine you're pumping hundreds of gallons a minute, of 800, 600, whatever, mud down the center. So, and a huge pressure. So you maybe doing thousands of PSI pushing at the surface. So you've got this sort of elastic medium. So if you, as it were, if you interrupt it, you create a pulse. And so downhole, what they use is literally have a siren, like a chopper. It's just like a fan. That's one way of doing it is basically the mud flow is sort of flowing through my fingers, there's a fan which sort of basically chops it as it goes through. And you're chopping the mud up and you're creating these pulses. And these pulses go all the way up to the surface. And then you have to sort of unpack it from all the noise that's going on with the mud pumps and so on. And you can get that to the surface, and you can sort of get up, bits, tens of bits per second, long wells, maybe half a bit, 2 bits per second, short wells, maybe you can get the higher bits. And then you've also got compression, so you can make better use of the transmission lines. So, 10, 20, 30 bits per second might also be available if you choose to use the higher bit rates and have the sort of surface decoding capability to get that information surface. Going downhole, it's worse. The hydraulics is against you. So in order to communicate with the tool downhole, it tends to be much slower. But it's remarkable, actually. We achieve what we do with such a low channel capacity between surface and downhole. And as I said, it's led to the evolution of the way the tools are. They've had to be smart, sufficiently smart enough to get on and be able to do what they do without too much advice.
Great, thank you. I have this answered your question, Ramesh John. So we have another question from Abdul Qadir. He's asking, how is the surface testing conducted prior to running the system in the hole?
Okay. It varies from system to system, but basically, everything is assembled. People get out the way. You run it. You run in hole a little bit, and then you can sort of. And this depends. It depends on the reliability of the system as well as to how much you're comfortable in not testing. But the sort of thing you want to make sure is that it's up and running, that the actuation is working properly. In the early days, what they used to do is sort of run in hole and then make the system sort of go through a sort of steering cycle, and you could look at the pressure waveform from the surface, because it was just very shallow, and you could see the actual pads or the actuators going in and out, so you could tell that it was working properly. It is, once you're actually in if you're not using mud pulse telemetry as a means, you've got to get the whole system in the well by that point. So people use different methods. So I think the more reliable the system is, the less surface testing is actually done. More confident about running it in. I mean, there's a lot of testing done on the tool before it goes in. It goes in the hole before you rig it up. Once it's actually on the rig, there's the minimal amount of testing to actually test the system, check the system is working.
Great, that's great. Thank you so much. Another question from Al-Qadir is that how far are directional sensors from the bits when running the RSS?
Yeah. It's there's a lot of competition as to how close you can get it to the front of the system, but you have to be realistic. And it isn't so much position; it's stiffness. So if you've got a long stiff assembly, it doesn't matter where you put your sensor. You're still measuring the same inclination as them. So you've got to take the stiffness into account. But there is advantages in having the sensors as close to the front end of the system, because you want to close the loop around it. And I was saying the spatial delay between the actuation and the sensor is important. It limits how tight you can make that loop. So generally, the sense for sort of to be sort of competitive, it needs to be within sort of 6 feet, let's say, of the system. The challenge for magnetometers is that you've got a lot of mechanical, your steering is mechanical, it's steel, it's lots of, and may also electrical power as well. And so the challenge there is, the inclinometer is the easy bit, it's the magnetometer that's the challenge, because your environment, mechanic, and your EMC, electromagnetic environment, are all things which are going to upset. So people tend to end up pushing it further and further back. And then you have this problem whereby you can steer okay in inclination, but you end up with sort of weavy behavior. And So the further you put that sensor back, the more unstable and the less able you are to hold a particular inclination, the more likely you are to get into this sort of weaving motion. So if you've got a stiff collar, it really doesn't matter where it is in the stiff collar until that's long enough to start bending, and then you have the problem. But a couple of feet, a meter, is really where you want them to be. But you have to ask the question about stiffness, not actual physical location.
Great, thanks. Thank you so much. Another question from Nabil is asking, he's saying that RSS should steer regardless of drilling parameters. So does this mean that even if we choose inappropriate drilling parameters, the RSS will work properly?
I'd like to say yes, of course. No, of course not. No, you can imagine if you think of the rig is a big crane and you've got thousands of tons of steel, you're supporting it. So if you let that all go, if you overload the system with the wrong parameters, you can break anything. I would say that they're sort of relatively forgiving. So you choose the right band of parameters, and it's good. And then you want the system to be resilient to a certain amount of shock and vibration. Stick slip is an interesting area whereby if you're turning at the surface at say sort of 150 RPM, the drill bit of the long elastics drill string will stop, and then it will spin up to 300 RPM, and then it will stop. And this could go over a waveform of about 5-10 seconds, depending how long it is. And so whilst it's spinning, the system's got to do its job. It's drilling forward, and so the actuation's got to be working to cope with it. And then when it stops, it's as a rest, I guess, and then it all starts up again. And on top of that, you've got all the shock and vibration. So you can certainly damage system, but the systems. The robustness is different across systems. You can see that in the way certain types of rotary steerable will avoid particular kinds of very harsh drilling environment, because it's just not fair on that particular scheme, where others end up doing more of the rugged work, which is more resilient to the drilling parameters. But weight on bit 1, RPM is another. And as I say, the drilling environment beneath the motor, mud motor, is not good. So your system has to be really spend a lot of time on environmental developments, shock and vibration, understanding how vibrations propagate through the system that make all your capacitors and devices pop off their boards. All those kind of things has to be worked out. So, and it tends to be, you arrive at these understandings through years and years of getting things which are broken, and you go back and you fix them, and you understand the mechanism, and you build that into your later generations. But it always amazed me that the drillers will always find a novel way to break your system at some point. There's this constant evolution whereby you think you've made it robust enough, and then there's, we'll drill a bit faster. And so they break something else. And despite what everybody tells you, all rotary steerable systems can be broken if you try hard enough or you're not careful enough. And that's one of the nice things about automation, is that you can get in control of these parameters, so you can work on the edge without constantly accidentally going over the edge, as happens when you just sort of leave it to a human being to do. So that's one of the possible advantages for automation.
Thank you. This is very insightful. So another question from Asia. She's asking, what is the difference between RNS and RSS?
RNS. Did I say RNS? I didn't
Not quite, not really. It wasn't mentioned.
I don't recognize the acronym. Maybe we can come back to that one.
Yes,
RNS.
sure. Okay, so maybe Asia, you want to clarify the abbreviation of RNS, because abbreviations can sometimes stand out to the same thing or to many things. So
I'm sorry.
sometimes alike.
said too fast and the sort of
Yeah.
no, I can't think of what it is at the moment. I'll come back to that.
All right, sure. So we go to the next question from Abdelkader, which is what are the criteria do we have to use to decide a motor or bit combinations that are run within the RSS?
Oh, yeah. So yes, I mean, it was quite early on in the history of Rotary Steerable that we realized that things will be much better if you could rotate the Rotary Steerable with a mud motor. So we found that you could get something like a 40% increase in ROP simply by adding a motor on top of a Rotary Steerable, which was sort of obviously worth having. The motor, there's the Rotary Steerables of different lengths, but there's a long stick out beneath a motor. Motors were originally designed just to have a bit on the end. And so you've got this drive assembly, which has evolved just to drive a bit, now dealing with, several tons of steering system on the end. And so you could imagine in order to not shear off or damage up. And so you can see that there's been an evolution in the ruggedness of the motor, the transmission, and the bearing housings. And generally, you want high torque, low speed motors. So a 7/8 type motor is where you get the high torque but to the lower speed, because there's no use pushing hard on a bit and the bit stalling or the motor stalling. It needs to still have that torque. So they tend to be long motors, low torque motors, where you also add the RPM from the surface by rotating everything from the surface. In terms of bit design, it's not so much the motor side of the story. It's a kind of bit of a compromise. I tend to regard the bit as a white noise source for lots of energy goes into the system. So it can be the source of the thing that sort of gives rise to high frequency torsional vibrations. It gets stuck, you can sort of slip and stick slip. All these things go on are things that you're trying to mitigate. So there's a confluence of many things on a bit design that you need to consider, and also you want to be able to steer the bit. And so in the early days, there was a belief that you wanted, what I was pointing out early with the anisotropy effect, that you wanted a bit which was high aggressivity. But that led to other problems. The bit will tend to whirl, open up the hole going over gauge is a bad story for steering, because the actuators can't do their job. They can't displace the center line of the system. Plus the fact you trash the bit as well. If that happens, cutters end up going backwards and popping off. So you want to make sure. So there's a lot of things that come together on the bit design. So the diameter of the gauge, how it's shaped, the distribution of the cutters, which are themselves also driven by the kind of formation that you're going to. So there's many things come together. So it's difficult to give you a straightforward answer. You have to ask the specifics of what is it you want to do. But I think the evolution of the gauge design within a bit to give you the ability to steer without losing stability, I think is an interesting area.
That's great. So it's basically dependent on the application, on specific application.
I mean, it's not a sort of a nice cut and dried answer. I mean, you need to get into the specifics, but I mean, the 3D cutters are now sort of higher torque, higher ROP. All these things are feeding back in sort of subtle way and sometimes not so subtle ways into the design of the system. But the combination of the bit, the motor, and the steering is here with us to stay.
Great, that's great. Thank you so much. Another question is that regarding the mud fluid, may the accuracy of the RSS be affected by changes in mud parameters?
I think where the systems are mud actuated or rely on mud turbines, which are now become more and more prevalent, then if you sort of put junk, tie wraps, bottle tops, that kind of thing, then that's it can be a bad news for anything, because things can get jammed. Heavy, very certain types of LCM, lost circulation material, can sort of get into the mechanisms and upset things if that's not thought through properly. The density of the mud, well, a lot of the internal mechanisms which are driven off mud, like turbines, like those things are also affected by the density of the mud. Things which are more subtle and maybe something that not fully not widely understood is the low gravity solids. It's the things that can't be taken out at the surface, through the shakers and the filters, but basically sand, very abrasive, and you've got hundreds of gallons a minute coming through your system, thousands of psi for days on end. Things will wear. You can pull something out and you're looking at it, it looks as though someone has beautifully sculpted it or melted it in some way, and it's just been eroded away. So the nature of the fluid in terms of low gravity solids on abrasion and erosion it can affect all these systems, and it's something that needs to be understood. It comes back to materials. To actually execute some of the mud actuated devices requires a deep understanding of that kind of mechanism and the materials and the flow paths, and there's a lot of CFD analysis done on how the flow patterns can impinge on different parts of the mechanism. But in terms of the chemistry, I think if you have sort of you can have high H2S. If you've got a lot of sulfur in the system, then when you've got systems which are rotating and bending, then you can exacerbate the cracking or fatigue of the system by sort of almost chemical action on the drill string, or things which are in a bend or constantly rotating, or rotating bend was about the worst thing you can do to a tube. Then you can end up with fatigue cracking due to the chemistry of the mud. Oxygen as well is another thing. You can also get bio effects, where sort of like bugs working on your system left uncontrolled. So there's a number of things that could go wrong. Again, it's a whole range of things. Depends on the nature of your system.
All right, great. That's great. Thank you for the extensive, enhanced answer. Another question from Nabil is that how can we detect that we're not following the targeted trajectory?
Yeah. This is a good one. So one of the things that you don't have GPS downhole. In fact, we're using a technique which ancient mariners used to navigate across the oceans. Literally, you sort of work out, the tool tells you what direction it thinks it's pointing in terms of inclination, azimuth, and someone is keeping account of the amount of pipe work that you're putting in the ground. And so you tie the two together. It's sort of a dead reckoning. You sort of try and work out, I put this amount of pipe and I've been pointing in that kind of direction, I integrate it up, I think I'm over here, kind of thing. And it sort of feeds very much on the accuracy of your sensors. And so, inclinations are good to better than 0.1 degree. Azimuth tends to be less accurate. So you end up with these ellipses of uncertainty that grow linearly as you go deeper and deeper into the well. That you only know analytically. You can't physically determine where you are by some independent wave propagation method. You do it sort of by dead reckoning. That's basically by and large the way it's done. So it's so keeping how much steel we put in the ground, what direction it's gone. There's lots of compensation to do with the sag and the behavior, where the BHA is lying. Lots of corrections of the stretch of the drill pipe, because imagine a holding thousands of tons of steel, everything stretches, so it isn't the length that you think it is. And temperature has an effect also, and pressure to some extent can also change. So all these things are little fine refinements, but basically it's dead reckoning.
All right, that's very insightful. Thank you. So we are left with I guess the last question. From Sammy is asking, what are the key features that make a system better than another in terms of efficiency, reaching the targets quickly and surely, along with cost and time saving? He's saying that is it the build rate and
Okay.
dog leg, sorry, capability, or just another criteria?
No, I risk another hour's presentation, so I'll try and keep it succinct.
Right.
I think one of the key features that make a system better. Okay, I mean, as this is an SPE slide, I'm not going to drop into a sort of a marketing presentation of any one type. So I'll try and keep it broad and as fair as human nature will allow me to do that. One of the first things is, particularly if you've not yet used Rotary Steerable, you want your first experience with the Rotary Steerable to be a good one. And so it's best to use a reliable system, something that's got plenty of miles on the clock in terms of reliability, so you can see within your organization that the Rotary Steerable technology works for you. You don't want to keep breaking down and having to sort of rerun it and then come back. You want to be able to drill a well and understand that if this technology, as it works, it brings value to you. And then so once you've got the understanding how to operate it, then you can say, well, okay, these guys are a bit more expensive, we'll go with these cheaper guys, but these guys are still learning, so I have to accept these systems will fall over. And there's a sort of that sort of cost side of things in terms of, okay, it's cheaper, but I'm going to sort of take twice as long to drill the well with all my other systems sitting by waiting to finish the job whilst I deal with this one particular problem. So that's sort of a balance, a sort of thought process that needs to be gone through. So reliability, efficiency, and certainty, because you want your well to be delivered in a set time. In fact, one of the big advantages of rotary steerable system, a reliable rotary steerable system, is the beginning and the end of your drilling phase is well understood. It should be faster than most other methods, but it all should be consistent if your system is reliable. There's a cyclic learning aspect to it, which so the first time you do it, you're learning a lot of things. You're learning the formation, you're in the rig, even the rig crew, and then once you're getting into the sort of cycle, then you sort of try and get the consistency, then you get the efficiency. Even without automation, it's the same story. You want to make sure that you achieve that you can sort of leverage what your system is capable of delivering along with the technology. Ease of deployment is good. The ability to understand whether the system is steering properly or is likely to fail earlier. There's lots of sort of reliability aspects which feed into this story. I mean, there are certain advantages for certain types of steering technique and layout, but then I'd get into sort of a marketing side of the story, and I don't want to do that.
Yeah, sure.
And it's not just, sorry to interrupt. Is it just build rate and dog leg capability? At the very beginning, it used to be you just barely made your 3 degrees per 100 feet, barely made your 5 degrees per 100 feet. But now the more advanced systems, you can do your 8s and your 10s and your 15s if you really want to trash everything behind you, and you can actually do that with these other systems. So it's no longer just build rate and dog leg capability. It used to be at the beginning, less so now. It's all those other things I've been trying to broadly put together that make for a good choice in the rotary steer reliability.
Yeah, that's perfect. Thank you so much. Let me add the question. He's saying basically, are turbines more suitable than natural bits? So he's asking natural diamond bits.
Yeah.
He's asking is the power source have a relation with the drill bit that we are dealing with?
Oh yeah, absolutely. So if you go back far enough in time, in Russia they were using turbines. Excuse me. They were using turbines. Basically use the fluid going through the impeller. It's fluid momentum turning the base. They spin quite fast. Hard ride. You know, it's a lot of abrasion, a lot of friction, a lot of heat that's going on. I mean, mud turbines can be very powerful, but you've got to have something at the end to cope with the speed. And really, only natural diamond was about the only thing that could do that. And you had to be drilling the right kind of rock as well. So if you drill sort of a sandstone or something soft, then the sort of diamond particles just don't have the depth of cuts to just clog off. You just won't use them. So certainly for the harder type of rock and so whole geothermal story, you can see the advantage in turbines. But generally, turbines are more complex mechanisms. They're more expensive to own and maintain. But they have this sort of speed difference. We go to mud motors, so they tend to sort of be, you have a sort of 1-2 mud motor, which vibrates like that whilst it's drilling. But you get the higher speed, but there's a mismatch. There's a gap between turbines, which sort of from about 1,000 RPM upwards, and mud motors are sort of like 3 or 4, say 300 less below. So there's this sort of windowed gap. And so everything below that, the evolution of man-made bits, PDC, which originally started out with roller cone, but spinning those really fast is probably also not a good idea. So there's nothing that's there's no evolution that I'm aware of bit technology which replaces the natural diamond wholesale. What is happening is the 3D cutters that although you won't run them at some turbine speeds as you would do natural diamond, their ability to cope with these harder, more aggressive, more stronger formations, because they are inherently stronger in themselves, is beginning to encroach on that speed. So you can imagine the sort of diamond, the natural evolution of 3D cutters getting deeper and deeper into that much harder drilling, which previously was only conscionable with turbines. So I don't think there's a lot of work going at very high speed drilling, and most of it is focused around the bits and the mud motor technology. But the natural, this interesting evolution of 3D cutters is extending the boundaries, so it doesn't overlap. Yeah,
Great.
I can see it's going on.
That's really insightful. Like, thank you so much. Like, thank you for the audience. Thank you so much, Mr. Downton, for your explanations and also for answering all the questions in a lot of details. So just to tell you and everyone that this session was recorded and it will be shared on our YouTube channel. You get its link in the chat. And we hope to see you in another exciting session. We hope to see you another time, Mr. Downton, in another session and also in another topic. Thank you so much, everyone. I hope you all a good evening. Thank you so much.
It's been a pleasure.
Bye.
Thank you very much for inviting.
Thank you. It was a pleasure.